Welcome everyone to week number 14. We are just now starting the class. We haven't done anything until now. You've missed nothing today. And this is on chapter 6 on two-way tables. And magically this table was there even before I started talking. So how phenomenal is that? What we have here is a case of projections in thousands for the year 2020 to 2021 of how many people are going to get various degrees in America for this year. And it's divided into two categorical variables. We divide it by the sex of the individual, women and men, not taking into account any issues of gender fluidity. So, apologies for any offense in that regard. I'm just doing the book's example. And then we have the degrees earned, associates, bachelor's, master's, and finally PhD. This is called a joint distribution because it is the distribution for two variables simultaneously. If I were to only care about the sex of the individual, how many outcomes are there for just the sex of the individual? How many? There's only two. So if I were to ask only questions about the sex of the individual without consideration for the degrees, then I might care about the total number of women, which I can get by adding the entries in that row, and the total number of men, which I can get by adding the entries in that row. And when I talk about how likely it is that a person's a woman or a man in this regard, I call it a marginal distribution because I am using the values that you can find in the margin. So you have the joint distribution, which are using the values of the two variables together. There's 8 entries there. Or I have a marginal distribution where I use the values in the margin. Of course, I can do two different marginal distributions. I can do one for the sex, whether it's a man or a woman. And what is the other marginal distribution that I can create in this scenario? For which variable?
For the degrees?
For the degrees. And in that case, I don't care about the individual values in the table, but I do care about the values for the different degrees. And I would use the values in that margin. So here and here, we have what are called, this is for both these guys, and this is for all of this. These are marginal distributions. And when I look at the numbers in the actual table, this is the joint distribution. There's one joint distribution, but there are two different marginal distributions. So if I ask, for example, the probability that a person chosen at random is a woman, would I use the joint distribution or would I use one of the marginal distributions? I'd use a marginal distribution. Oops. And what would that be equal to if the total, which by the way, they also give me the overall total, is 3,905,000, so 3,905,000. What would be the formula for the probability that a person chosen at random would be a woman? I don't care about the actual value. I will need a calculator for that, or at least I should use a calculator for that. But what would at least be the fraction? The probability that a person chosen at random is a woman would be 2283 divided by 3,905. Excellent. It's the number of women divided by the total number. Notice that I don't use any of the information in the table for that. I only use information in the margin because I am using one of my marginal distributions. Right? Yes, no, maybe so? So far, I really have 3 distributions. The joint distribution is a function both of the sex and of the degree. And I have two marginals. One marginal distribution is a function only of the sex, and one is a function only of the degree. I'm using the letter F in all three cases, but they are different functions. The joint uses both S and D. The marginal uses just S or just D. I only care about the sex, I only care about the degree, and I don't care about the two of them together. So joint distributions, kind of important. Marginal distributions, kind of important. But there's one other type of distribution that I can do here, besides the joint and besides the marginal. And the other type are the conditional distributions. In this case, I want know the likelihood of getting a certain sex given a certain degree, or the likelihood of getting a certain degree given a certain sex. So the third situation is likelihoods of one outcome in one variable given that we have a certain outcome of the other variable. So there's actually in total 5 different distributions that one can talk about when dealing with a two-way table. The joint distribution, the marginal distributions, or the conditional distributions. Now, in this example that we have here, how many joint distributions are there? Not how many outcomes are there for that distribution, but how many actual joint distributions do we have? The answer is 1. We have the 8 different values. Those are the 8 outcomes for the joint distribution. There's 1 joint distribution. How many marginal distributions do we have? We have 2. 1 if we care about the sex of the individual, and 1 if we care about the degree of the individual. Now for the fun one. How many conditional distributions do we have here? Spoiler alert, it's not 2. How many different conditional distributions do we have? It's not 4.
Is it 8?
It's not 8.
Is it 8?
It's not 8. It's not 5. Are we just guessing random numbers now? Are we, did someone say 0? Okay, well, it's not 0. I can tell you that much. So I'll tell you this. I'm looking at all these numbers here, and I do see the correct answer, but I want to make sure that the person who wrote the correct answer knows that why it's that actual value and not just guessing it correct. But I do see the correct value there. How many conditional distributions are there? So how many different things can we condition upon? If you condition on the sex of the individual, how many different ways can you condition? I could say, what's the likelihood of getting an associate's degree given that we're dealing with a woman, or given that we're dealing with a man? So there's 2 conditionals when I condition upon the sex of the individual. How many different ways can I condition if I'm conditioning on the degree of the individual? Four, depending on if I condition on associates, or on bachelor's, or on master's, or on the PhD. So overall, how many different ways can I condition? The answer is 6. There are 6 different conditional distributions. And those distributions are basically the columns and my rows in my table. Because there's 4 columns and 2 rows, there are 6 ways that I can condition. So there's actually 9 different distributions in this two-way table. Of course, you don't really have to think of it like that, but there are 9. So let's do some examples. What's the problem? This is an example here before, so here's another example. What's the probability of someone getting a PhD given that they were a woman? What is the probability of getting a PhD given that you are that person chosen was a woman? And I'm not looking for the answer because I don't have my calculator handy. I had to reach across the table and I'm just too lazy right now. But give me the fraction for the probability of someone getting a PhD given that they were a woman. So that's it. It's 97 over. Now, I see people writing over 39 over 5. But if you do it over 39 over 5, you're not taking into account that we are conditioning it upon the person being a woman. If we know for a fact it's a woman, then the men are irrelevant for the problem. I don't condition on 3905. I condition on 2283 because I'm only conditioning it upon the women. That's my known. That's my given. It's definitely a woman. So Flower got it. It's definitely a woman. And of those 2283 women, 97 of them have PhDs. What's the probability of being a woman given that the person got a PhD? In fractional form. Yes, 97 over 184. If you're conditioning it upon the person getting a PhD, that means you know for a fact the person got a PhD. There's 184 of those, and of those 184, 97 of them were women. So it's much more likely that a person was a woman given they got a PhD than the person got a PhD given that they were a woman. Or at least these are the projections. Ideally, these numbers both go up. I wrote that fraction in the beginning, but was unsure. Well, I would say trust your instincts, but only trust your instincts if your instincts are right. If they're wrong, you should not trust them. So that expression, trust your instincts, is really only right some of the time. But does that make sense? How to do these? I mean, that's pretty much it for 6.1 and 6.2. There's really not much else in there. I mean, I can do more examples, but the examples are exactly the same. I mean, let's just do one more just to make sure we solidify it. What's the probability of someone getting a master's degree given that they were a man? $329 over 1622. So Flower, you wrote 460 over 789. Let's think about that. First of all, 460 was with women, not with men. But even if it was with men, you're conditioning it the wrong way by going, I saw it wrong. Okay. Now, follow-up question. What's the probability that a person got a master's degree and was a man? Now we're not conditioning upon it being a man. We're considering the possibility that it wasn't a man, just in general. What's the probability that a person got a master's degree who was a man?
You want us to type it in the chat?
Yeah, or you can say it.
Well, I'm just gonna guess. My best guess. Would it be
Okay. No, give me your second best guess.
Would it be 329 over 3,905 because of being like from all of it?
That's correct. Excellent. We are using the joint distribution there. We're going back to the beginning and saying there's 3,905 people. I'm not reducing that because I don't have any extra knowledge. So any one of the 3,905 people is easily chosen as anyone else. And of those, how many of them are going to get their masters and be a man at the same time? And the answer is 329 of them. So when we condition, we change the denominator because you're limiting your attention to only a subset of the original. Does that make sense? Questions? Comments, remarks, metaphors, allegories, similes? Are there any other synonyms that I forgot? I'm sure some of you are English majors, right? Or know English. Metaphor, allegory, simile. That's all I got. All right. Now, section 6.3 is on something called Simpsons Paradox, discovered by Homer Simpson. Simpsons Paradox. Nobody laughed. Yes, it was not discovered by Homer Simpson. He was just out eating ham somewhere. So no, this is a very famous paradox by an actual mathematician. So here's the question. Do medical helicopters save lives? Right? You're in an accident and a helicopter comes and rushes you off to the hospital. And the question is, do medical helicopters save lives? So data was taken and we have the following two-way table. The victim either died or lived. And went either by helicopter or by road, by ambulance, whatever, or maybe like a car. I don't know, anything other than a helicopter. And here are the values taken from my data. So those four numbers comprise the joint distribution when we consider method of travel together with outcome. And if only I care about is the method of travel, I would look at the margins on the bottom because all I would care about is the total down here and the total over here. And if all I cared about was whether they died and whether they lived, then I would care about the margins in the rows. And I get 324 and 1,170. No, not 1,100. 976. So this is the data. So question, what's the probability that a person lived given they went by helicopter? Yes, 136 out of 200, which is 68%. So 68% of the time, the person lived when they went by the helicopter. And what's the probability that they lived when they went by the road? Oh, 840 out of 1,100, which was approximately, when I did my calculator, 76.4%. Certainly seems that a person has a better chance of living when they go by road than when they go by helicopter. So why do we even send helicopters? The data suggests that you are much more likely to live when you go by road. Not much more likely, but 8%, still 8 out of 100. It's still a nice amount of people. So it certainly seems that you're more likely to survive if you go by road than if you go by helicopter. So why do they even send the helicopters now?
Because some places can't be reached by cars.
You mean like hospitals on water or something? What do you mean? When people are stuck in risk situations, rivers, forest. Okay, well, let's assume for the sake of this argument that both of your explanations don't apply because every one of these people was in a situation where they could have gone by helicopter and they also could have gone by road. Let's just assume that for the sake of this situation. Why ever go by helicopter if people are more likely to live by going by road? Helicopters are cool. So those answers are, helicopters are cool. I've never actually been in a helicopter, but it seems to be like it would be cool. But you guys are not hitting upon the right reason. So let me go ahead and write out the data in a slightly different way. We're going to have two-way tables. Lived, died, and lived, like before. And helicopter and road, like before. But this one will only be for serious accidents. Serious accidents, not little minor things, but serious accidents. Versus a two-way table for died and lived and helicopter and road. And this one is going to be for minor accidents. Let's look at the data broken up by the seriousness of the incident. And we have the following results: 48, 52, 60, 40, 16, 84, 200, 800. So question, for serious accidents, what's the probability that they live by going by helicopter or live by going by road? Let's do the helicopter first. What's the probability that they live by going by helicopter for a serious accident? Anyone? 52 over 100, that's 52%. And how about live, did they go by road? $40 out of 100, 40%. Oh, look at that. For serious accidents, you have a better chance of survival going by helicopter than you do going by road. What about for less serious accidents? What's the likelihood of living by going by helicopter? $84 out of 100, that's 84%. And what's the likelihood that you live by going by road for not so serious accidents? I don't want to call it minor, because if it was minor, nobody would ever die. Let's call it less serious accidents. So what would that be? 800 over 1,000, which is 80%. So here is Simpson's paradox. Wait a second, this is very strange. If you focus only on serious accidents, what's better, helicopter or road? In terms of likelihood of surviving?
Helicopter.
Helicopter. If you only focus on less serious accidents, what's better, helicopter or road?
Helicopter.
Helicopter. You lump them all together, what's better, helicopter or road? That's not what the data says. Look at the top.
It's road.
Road. Wait a second. If you do them, wait, hold on. You do them one at a time, helicopter is better for each. You lump them all together, and now road is better? Enter Simpson. What? What? That's Simpson's paradox. How is it that individually the same one could be better, and then when you lump them all together, it now becomes worse? Leanne, you were saying something?
Yeah, I just had a question. For when you broke them up, where did you get those numbers? Did you like just divide everything?
The numbers in the boxes were provided from the data taken in the survey. So these are not my numbers. These are all fixed. So again, does everyone see the seeming paradox here? That when you look at when you divide up the data into two small sections, in each section the helicopter is better, but somehow when you lump them all together, the helicopter is worse. This is Simpson's paradox. So what's the answer to the question? Why is this not really, paradoxes are things that on the surface seem like they make no sense. And then by analyzing them, we come to a deeper understanding, and our understanding of the whole situation is improved. In physics, there are things, for example, called the twin paradox, which was stated as a paradox about how is it that two twins can age at different rates, and turned out to be the way reality is. Two twins can age at different rates. In logic theory, we have Russell's paradox. Russell's paradox was so paradoxical, for lack of a better word, that it completely revolutionized the landscape of mathematics about 100 years ago. Just changed the very foundations of mathematics for a very simple seeming little question that this guy Russell came up with. Simpson's paradox is another example of a situation where on the surface seems like they're very weird, but this one is not as groundbreaking as the other two because the answer is actually very clear. What is the actual value of the percent who lived by going by helicopter in the serious accident case? What's the actual value? It's 52%, right? And what's the actual value for the less serious case? %. When you lump them all together, we're in a sense taking an average of the two. but it's not a real average because the samples for serious and not serious are different. I only count 200 serious accidents, but I count 1,100 less serious accidents, which is why the probability of living by helicopter is shifted from the exact center. What's the average of 52 and 84? When we average them, 52 plus 84 and divide by 2, well, we get 68%, which is the exact, what? Oh, of course. Sorry, that's the exact average because for helicopters, it's the exact same sample size. There was 100 of each. 100 serious accidents by helicopter, 100 less serious accidents by helicopter. So the average is right smack dab in the middle of 58 and 84. It is 68%. But now look at the numbers for roads. What is the probability of living if you go by road for serious accidents? %40. And how about for less serious accidents? 80%. If I were to average those, you might think it's 60%, but it's not. Why is it not 60%? Because the number of less serious ones is 1,000, and the number of serious ones is 100, which means the average is weighted significantly more towards 80, which is why it ends up being 76.4%. It's because of a weighting issue. The sample size differential sends one up to 76.4, thereby beating the 68%. It's completely because of the huge sample size that the value of living by road is so high in the lumped together scenario, 76.4%. But if all I did was I look at these, I'd be completely missing the lurking variable behind the scenes of the seriousness of the accident. So when I take those into account, I see very clearly that helicopters are always better, whether they're serious accidents or less serious accidents. Because in theory, the only difference between them is how fast you get to the hospital. For a helicopter, you don't have traffic, so you get there faster. That can't be a bad thing. Does this make sense? On tests, you will never have numerical questions involving Simpsons Paradox, but you could have a qualitative question. I saw in the final last year something along the lines of a multiple choice question where it said, what is it called, this idea that you can get different results if you lump them together or not? And it was like, well, is it the central limit theorem? Is it the law of large numbers? Is it Simpsons Paradox? Or is it this? And it's like, oh, it must be Simpsons Paradox. And that was it. You're not going to really have real questions for these. Does that make sense? Yes, no, maybe so? Okay. So chapter 25, which is the only other chapter we got to do, it shouldn't take more than a day. Like 6 shouldn't take more than half a day. So we're actually going to push it off till Thursday because I want to answer questions and I want to give you time to do this survey. So we're going to end really early today. We're going to end now. So I'm going to first stop sharing. First, are there any questions on what we did today? That's the first question. Okay. Oh, wait. We have a test on Thursday, don't we? I totally forgot about that. We have a test on Thursday. That's okay. We'll finish on Tuesday then. We'll still have a day of review on the Thursday following, but we will finish on Tuesday, chapter 25. The test is comprehensive quiz number 3. I can't call it a test because if it was a test, you'd have to be on campus. So it's a comprehensive quiz number 3, and that is on Thursday. It is a 90-minute quiz which will open at precisely 4 p.m. and close at precisely 5:40. So you have a 100-minute window to do a 90-minute comprehensive quiz. So don't be more than 10 minutes late. How many questions? Great question. I don't know. I haven't looked at it yet. I don't write these quizzes, so I don't have to look at them. The last day of actual class is next Thursday. That's right. Next Thursday is the last day of actual class. So on Thursday, you do not have to come. Just be online. Then we'll have our last teaching period on Tuesday. And then we will have our review for the final on Thursday. Know what? No, you're upset that you're never going to see me again? What are we knowing? I know, it's so sad, right? I know. I actually, just a few minutes ago, was in this room with some students here at school, because I'm on school right now. And, sometimes like someone's looking at you, so you look at them and they don't stare away. And so you don't stare away. And it's kind of like, what's going on here type situation? Like, why is this person staring? So I'm pretty sure it was one of my students, but if it's not Leanne or Mary, I don't know what any of you look like because none of you are ever on camera. So it's like, I'm like, is that one of my students? I don't know. It's a great question. I don't even know why that came up in conversation, but in my head, it made a lot of sense. So as a final, you should feel, well, yeah, I see your icon, but do you actually look like that? I don't know. I mean, that could be like, some thumbnail from the internet for all we know. I don't know where that came from. I don't know what you really look like. By the way, speaking of which, tisk. That's a TSK sound. There's no K there though. We should spell it differently. Anyway, where am I going with this? So where is the final taking place? All that information will be provided to you as we get closer to the end. Because I just don't have an answer. I do have an answer. I just don't want to look it up right now because I'm too lazy. But if you go to Portal, it should be on it. Formula sheet. I'm 99% sure a formula sheet is allowed. Or even possibly open notes. I'm 99%. How do I prepare for the comprehensive quiz? That's a great question. How do you prepare for the comprehensive quiz? And wait, nobody go anywhere yet. I have some announcements to make. Hold on. But if you look in the book, on page, in my book, I think you guys have the same book. Yeah, chapter 24, pages 542 to 549, the test yourself section, there are lots of questions that would be a great review for this stuff, 100%. That's a great place to, I wouldn't say to start because obviously you guys are not starting now since you've been studying for a long time. The practice quizzes are great. The questions are always similar. I love that. I do have a bunch of emails here about this class from my boss. So let me go ahead and, okay. So we have a final exam study guide. I'm going to get that out to everyone. So this is not for,
Professor,
yeah.
are you going to let us know before the actual final exam if we're allowed to bring our notes?
I'm sorry, say that again, please. Before what?
You said you weren't sure if it's open note or anything like that. Are you going to let us know before the actual exam?
Yeah, of course. Yeah,
okay.
Of course. Luis, if you haven't opened the book since the beginning of the semester, I'm not sure if that's funny or sad because you should always be reading from the book as we go along because no matter how good or bad a teacher might be, having a textbook written by 30 people, edited by 70 more, proofread by 66 more, and so on, that's gone through multiple revisions, and they've picked exactly the words to describe something, that's going to be a pretty good way of explaining something compared to someone who's just talking and says, oh yeah, by the way, this is true. So I always, and this is for every class, I always recommend reading books. I was always a big book reader myself. And definitions and formulas are wonderful. Anyways, the online book is very convenient. Okay, so none of these emails pertain to the comprehensive quiz number 3. They're just about the final. So I will be posting a sample study guide for the final, which will be relatively similar to the actual final that you're going to have. Meanwhile, that's good. That's actually good. Meanwhile, I just posted a link in the chat, www.csun.edu/SEF.